Good evening, everyone, and thanks for joining us tonight. On behalf of the Encounter, I would like to welcome those here in New York and those following us online. My name is Maria Elena Monzani. I'm a lead scientist at Stanford University and an adjunct scholar at the Vatican Observatory. I will moderate this event. Before starting, I would like to thank the Benedictine College for its generous support in organizing our conversation. We have two exceptional speakers tonight. I'm very excited for all of you. I will introduce them quickly and then give the stage to them. Stefanie Milam is the James Webb Space Telescope Deputy Project Scientist for Planetary Science. Her expertise is in the compositional studies of primitive bodies, namely comets, and uses ground and space-based facilities to understand their connection to the formation and evolution of planetary systems. Massimo Robberto is full scientist at the Space Telescope Science Institute in Baltimore, and is currently instrument scientist for NIRCam, the near-infrared camera for the James Webb Space Telescope. In the past, he has led a number of programs with the Hubble telescope, including the Treasury program on the Orion Nebula cluster. This is the largest Hubble program ever dedicated to the formation of stars, and has produced some of the most beautiful images ever made by the Hubble telescope. Stefanie, why don't you get us started?
All right. Thank you so much for that lovely introduction. And thanks again to everybody for being here. I'm going to get us started and let you know what we've been doing with the James Webb Space Telescope. But first, I want to give you a little bit of background. So this telescope is actually a long time coming for us. It's known as the successor to the Hubble Space Telescope, but I'll tell you, and Massimo will tell you, a little bit about why it isn't exactly a successor to the Hubble Space Telescope. So once Hubble was launched, we had challenges presented with us. This was a whole new view of the universe, and we were seeing things that we hadn't ever seen before with fantastic resolution and sensitivity. You've all grown up and know the Hubble Space Telescope images just as intimately as I do. But we already knew, even within the first few years, that we wanted to do better, and we wanted to know how to do better. So a group of scientists were actually pulled together, and they determined that we needed to go to longer wavelengths. We needed an infrared telescope that was just as capable as the Hubble Space Telescope. So we had to build one that was a telescope that's over 100 times more powerful. We needed a telescope that was over 50 times the resolution of our former infrared space telescope, known as the Spitzer Space Telescope. It needed to be comparable in size to the largest ground-based telescopes at the time, but because it had to be big, that means we had some engineering challenges, which I'll talk about a little bit. We wanted to send it 1 million miles away from Earth to the second Lagrange point because it's an infrared telescope. We're looking for heat signals. So the heat from the sun, the Earth, and the moon needed to be avoided as best as possible. We had to have a cryogenic operating telescope, and basically the best instruments that you could possibly build. And I'm sitting next to one of our instrument scientists, so you'll get to hear some of that too. So let's talk a little bit about Hubble versus the James Webb Space Telescope. It is huge. It actually stands about 3 stories high. The sun shield, which is the large silver structure on the bottom here, is about the size of a tennis court. Whereas Hubble, the whole space telescope, is about the size of a public bus. So we have a mirror for Hubble that's 2.4 meters in diameter, and the James Webb Space Telescope is about 6.5 meters in diameter. Hubble was launched in the 90s. We launched the James Webb Space Telescope on Christmas Day of 2021. Hubble has been operating successfully for over 31 years now. JWST was launched with the mission expectation of 10 years, but after our beautiful launch, we now know that we have 20 years. You can see that the mass, even though we have an extremely large telescope, was lightweighted so that it's actually half the mass of the Hubble Space Telescope, which is quite significant and definitely an engineering challenge that was met. And because we're 1 million miles away from Earth, we're very cold. So basically, this is a really big telescope. This is a picture of a scale model at NASA's Goddard Space Flight Center, where I work, showing you part of the team. So we have this huge telescope, and we have to figure out how to put that into the fairing of a rocket. So we had to present ourselves with the engineering challenge of how to fold a telescope. So sometimes you'll hear JWST is now called an origami-like telescope, and that's because we have to fold it up. So to do so, we fold the mirrors, the three sets of 3 mirrors on the side fold back, the secondary mirror folds up, and then our sun shield pushes in and then folds up on either end so that we fit nice and tight into the fairing of an Ariane 5 rocket. And this is what it looks like when it's folded up. And that's actually me standing in front of the telescope about a month before we sent it down to French Guiana for launch. It was huge. I cried.
10, 9, 8, 7, 6, 5, 4, 3, 2, unité, top.
So we launched on Christmas Day of 2021. This was the most terrifying moment of my career.
Decollage, liftoff from a tropical rainforest to the edge of time itself. James Webb begins a voyage back to the birth of the universe.
Spending over 20 years to build a telescope and then putting it on a rocket is very terrifying.
Pitch program reported.
A $10 billion telescope. This is an operations center in Baltimore, Maryland. Watching intently, I believe Massimo was there. I was sitting at home in my living room with my dog, my boyfriend, and my niece.
Confirmation of observatory separation.
Our launch was exceptionally nominal, and I think nominal just doesn't even describe it. It was absolutely perfect. And in fact, it was so perfect, we got to see our first deployment. And that was a complete surprise to us. After launch, we were fortunate enough to have a camera on the rocket itself showing the spacecraft, as you see here, separating. If the launch wasn't as perfect as it was, we would have to do a couple of tiny maneuver corrections, burn some thrusters to make sure the telescope was going in the right direction. But we didn't have to do that at all, and we saw our first deployment, which was the sun shield, the solar panel. So we were off of battery power almost immediately, which was fantastic and demonstrated how successful this mission was already going to be. So with that, I'm going to turn it over to Massimo. Oh, nope, I'm going to talk to you about deployments. Okay, so once we launched, we had about a month of terror. We had to go 1 million miles away from Earth, and we had to deploy the entire origami telescope now. So we have a series of 40 deployable structures, over 178 mechanisms to make them move. Not all of them had backups. There were lots of sleepless nights for an entire month. I will tell you, this was one of the most successful remote deployable sequences NASA's ever had, and now we know how to build large space telescopes. Because of the success of the James Webb Space Telescope, many future generations of even larger space telescopes will likely come. So you can see it was a very complex sequence. Everything worked perfectly, and we were on our way to 1 million miles away from Earth to the second Lagrange point. So we have 5 Lagrange points. These are gravitationally stable points between the Earth-Sun system, and we are the one that is the opposite side of the Sun, and we go around the Sun with the Earth in an orbit. And this is a fun little picture that you can actually see the telescope on its journey out 1 million miles away from Earth, taken from telescopes in Baltimore, Maryland. So what it looks like as we go around the Earth is we're in this orbit, and we're basically with the Earth going around the sun. But it means the bottom side of our telescope is always has access to both the Earth and the sun. So we have a small solar array for power, and we can communicate with the Earth continuously with our communication system. Okay, now I'm going to turn it over to Massimo.
Okay, thank you. So I'm going to tell you something about how the telescope is actually built, the main elements, and how to achieve what we need. Just to clarify, all of us are at the wavelength that we observe with the Hubble. We are all shiny bright, but we, in the sense that each one of us, or each piece of matter, this microphone, everything at this temperature emits gazillions of photons. So if you want to look a few photons that have traveled across the universe from a remote galaxy, is a problem to do it from here. We need to cool down things to crazy low temperature, like 230 degrees centigrade below zero, 40 Kelvin. And this is what we do with the Webb. It's an ultra cold telescope. Now the problem is that the sun, like the Earth and the Moon, are shiny bright. They warm up things, so we need to keep isolated this cold side from the warm side, which is the one facing the Earth, the Sun, and the Moon. So here in this graphics, the Earth, the Moon, and the Sun are on the bottom, and the telescope is on the top. The top is isolated, is shielded by these 5 layers. It's like an umbrella that keeps the two things completely separated. And the top part is basically just exposed to the cold universe. The universe is even colder than our temperatures. It's 270 degrees below zero, 3 Kelvin. So in this situation, we reach our extremely low operating temperature. Apart from that, the telescope is rather conventional, you may say. The telescope is a machine that receives light from sources which are at an infinite distance. So parallel rays coming from each point of the sky with tiny different angle, and they are all concentrated on small points on what we call the focal plane, which is where we take the images. This is basically the principle. Collect these parallel beams and focus them on the image of these objects. So in fact, once we collect the points, we can split the light, send the light to different instruments and to be analyzed in different ways. There are 17 observing modes, 17 ways to analyze light, infrared light on the Webb. The instrument that I mostly followed is called NIRCam. In this picture is the central one, the gold one. But there are other 3 around that serve different purposes. NIRCam has this structure that is shown here. Is like 2 sides, one on the top, one on the other. On the bottom, they are basically the mirror image of the other. Why 2? Why is built in this way? Because NIRCam has a double task. On the one hand is the instrument that takes wide field images of the sky, so it's the prime imager. But on the other hand is the instrument that keeps the telescope together, aligned, because as we have seen, the mirror is, and I will return on that, the telescope is built, the giant mirror is not a single piece, it's built with 18 segments, and these 18 segments need to be kept together to form like a single surface, the surface of an ideal mirror. And this is done with instrumentation that is built on NIRCam. So NIRCam has to serve the telescope, keep it in good order, and this is important not only for us, but for all the other instruments. So it's like a servant that keeps the machine aligned. So there are 2 of them, because if you miss one, if one stops working, the other one is still alive. So it's for the type of redundancy that we like to have in space mission. And so NIRCam is not only capable of looking at the sky, as we will see, but is capable of looking at the telescope and making sure that the mirrors are in place. And this is one of the first images we have taken where NIRCam, the instrument, is actually looking at the mirrors themselves, the 18 mirrors. And what is happening here is that one of the mirrors is actually exactly pointing to a bright star and therefore is illuminated. All the others are just still of alignment, so they are looking at the dark sky, there is nothing bright, so they look less bright. But analyzing this type of images and others, even a little bit more exotic, so to speak, we were able, as I will show you, to align the telescope. that's the selfie of the mirrors is something that you can easily imagine, because it's really the reproduction of the mirrors that we were seeing that from the ground. So this is a selfie as well that Stefanie made in the clean room. So I have no time to tell you about the fascinating choreography, but took a couple of months to put all the mirrors together. We were talking about capturing them, understanding where they are pointing, and make sure that they are eventually co-aligned and produce all the light that they see is concentrated on a single point for each star. It's like a little bit herding cats at the beginning, because the mirrors were actually pretty well aligned at the beginning, but the launch, as we have seen, is a terrific environment. The vibrations are such that things start to move around, and therefore we had to move. Each mirror has 6 actuators, so there are degrees of freedom, and we need to understand each one of them for each mirror what it does. So it's been quite time-consuming, and the choreography has been rehearsed and tested for years. So when we need the time, we know exactly what to do step by step. It took only 2 months to do this. And this is one of the first images. This is how a bright star appears immediately after launch. We knew at this point that the telescope was alive, the detectors were alive, but clearly you see 18 stars, each one a little bit bad, elongated, misaligned, out of focus, because we need to put together 18 telescopes to make sure they work like a single one. So this is how we started, and then moving the mirrors and taking day after day images and going back and forth, we started getting first the 18 segments to understand where each mirror is pointing, actually, so like capturing what is looking, and then focusing, which is the middle one, and then finally putting all of them together so we get a single image from the 18 mirror. That is not actually the end point, because it's not only that the mirrors, the telescope has to collect the light and put in a point, but we want really all these surfaces to be exactly on the ideal, perfect mathematical curve that produces a single mirror, because then a more subtle phenomenon, what is called interference, plays, and you get the ideal theoretical image of a perfect 6.5-meter telescope. And this is what happened when we saw that. Suddenly, the star became incredibly bright, incredibly sharp, and due to the sensitivity of a 6.5 telescope, what happens is that together with our bright star that we were looking at, suddenly we see all these galaxies popping up from the background, because the telescope reaches immediately a sensitivity that was, even if you do the math and you do the calculations, I tell you, there is no way to beat the surprise that you see when you really realize what you have in your hands, the level of sensitivity of this telescope. The galaxies seen were infrared galaxies that with the Hubble we would have had a terrible time reaching them, and they were just showing up everywhere. This is another of the first images, just to give you an idea of the change. This is not a single star. This is still with the mirrors poorly aligned, pointing the Magellanic Cloud, a region full of stars. And here, everything gets messed up, because all these stars are seen 18 times out of focus. This was the real beginning. This was a great image for us, because we understood that the mirrors, the instrument, everything was working, just needed alignment. And this is what happens at the end. This is the same field. After everything is on focus, after these months of work that lasted about what was 1 year ago, in these days, we started producing these images. Now, you can imagine day after day for us, at some point you are in the control room around there and you see clapping, because every few hours there was one of these steps, and we were just going after step in this choreography rehearsed for years. Things were going well and well and well and well, and seemed better and better and better. It was really a fascinating time, the highest point of our career. And this is what happens where the instrument NIRCam has aligned the telescope, everything is in order, then all the other instruments start to see. And this is a beautiful picture, because show the incredible quality of all the other instruments. Now, I remember I show you the 4th at the beginning. There is a 5th one, which is like a servant to all of us to keep the pointing. And this is how they all behave in the right way. This is an image that shows you the change, actually. Webb is not the first infrared telescope that we had. The NASA had a cornerstone, a very important mission. Spitzer was a fundamental satellite that we relied, as infrared astronomy has been built on Spitzer for decades. And this on the left is the image that we had from Spitzer, from a camera at 8 micron. And you see now the change that we get with Webb is basically the same wavelength and gives you an idea of the dramatic change in sensitivity. And all these images taken with the Webb that I'm showing you are really like snapshots. It's not that we have made to produce this. This is not a giant investment of time. It's just the way the telescope works when you spend a few minutes on a celestial field. I guess you can take over and okay. Show now. I've given you an overview of how the telescope has been built, and now maybe some recent results. Stefanie may show you something new science.
Thanks, Massimo. So last summer, we finished commissioning the telescope, and it was 6 months of just endless nights, making sure everything was beautifully aligned, as Massimo just showed us. And so last summer, we had an event where we wanted to show the world how well the telescope actually performed. And so we released a series of images. The president actually released our very first image, and it was called JWST's first deep field. So what you're seeing here is that what that image actually looks like in Hubble's eyes. So with the Hubble Space Telescope, we actually observed the same region as the James Webb Space Telescope did. And this particular image with Hubble took, I think, 2 weeks worth of Hubble time. It took a considerable amount of time to do. With less than 8 hours, JWST surpassed the sensitivity of the Hubble Space Telescope. You can see hundreds of thousands more galaxies. And I want you to think about one thing. This image, the size of this image, if you had a grain of sand and you held your arm out at arm's length and you put it against the sky, that's the size of the sky that we're actually imaging. And we see thousands of galaxies within a grain of sand. So just the mere vastness of what we are already seeing, the first image released with JWST already blew us away with the capability, and 8 hours. This is a blink of time. We have a 20-year mission, and this is what we are able to do in 8 hours. So this was absolutely mind-blowing. Also, what's fantastic about this image is we are getting to see real physics and real science in action. So the center brightest galaxies, the 5 that are sort of right along the line under that bright, sharp, pointy star, are galaxies that are so massive that they're actually bending light around them. And so some of these galaxies that you see that are almost streaked and smeared, they're actually galaxies that are much, much further away, and the light is being pulled by the massive mass of those other 5 galaxies and being stretched around them. So this is called gravitational lensing. This is something Einstein told us that we would be able to observe. We do observe it. We have so with the Hubble Space Telescope, but almost every field we look at now with the James Webb Space Telescope, we're seeing lensing in some form of another. It's absolutely fantastic. So this is just giving you sort of a pictorial representation of what I'm trying to explain about light coming and being bent around. I'm going to let Massimo talk about this next image because he has a little bit of passion for it.
So one of the first things that we did immediately after commissioning, before really going into science, was to demonstrate to the community, to our colleagues, to NASA, that everything was in order. So we picked up a few secret targets. We were under embargo. We cannot say what they are. Only a very small group. And a very small group of us met every day for like 45 days at the end of the first 6 months. And this data, this science observation started to come, and we were observing a few selected fields. One of those was a star-forming region in Carina. This is how the nebula looks like seen from the ground. It's a giant star-forming region, about 6,000 light years from us, so not too far. It's in our galaxy, and of course it's huge. No, we have said how small is the telescope is sort of a microscope if you think about how much area we can look. And even with our largest camera, we cannot really have this type of vision, which is something you get from the ground with a small telescope. We pointed the region up there, like a satellite star-forming region in this giant area. And we actually, with our instrument, managed to get a snapshot of that area in the red rectangle. So this is where we pointed, and we took a series of images. This is the result of the final image. That is one of the most spectacular visions we ever had of the star-forming region. What is happening here is that there are bright stars, giant stars that just formed. They are out of the field, they are above, and they are blowing away ultraviolet light mostly, and this ultraviolet light is eroding the molecular cloud, the dust, the material, where new stars are actually forming. So it's a race against time between this destruction from the ultraviolet light coming from the top and the fact that inside here new stars are trying to form. Now, I have to say, technically, we don't take that image so easily. The instruments, our instruments only work black and white, because when you want the ultimate sensitivity, you don't take color images, you take images in black and white to get the last photon on your detector. The way you get the light is that you put a piece of glass, a color glass, so to speak, or a bit more sophisticated, but that's the idea. You put glass that can only transmit certain wavelengths. So you do again and again the same picture, changing the yellow, the blue, the red. In fact, you are working in other colors, other wavelengths in the infrared. But this is what you get at 3.35 micron. This is what you can do. Once you get the image, you tell to a technician, an artist, let's use this as your blue image in your computer. Then you change the wavelength, you get another black and white at 444 micron, it's the green, and then you can get a third one at 4.7 micron. So different images, they are produced in these colors, which are those that our eye can see, but they come from different wavelengths. And only when they are combined, you see this type of results. So this is the standard technique for us to obtain these images. Now, each filter that is taken is not taken for this image, is motivated by a deep and well-thought scientific question. Is our art as astronomer to decide in the 29, 30 filters that we have on NIRCam, for example, what are the 3, 4, 5, 6 that we want to use to answer certain scientific questions. But once you get the observations, then artists can produce these spectacular images. Now, here, I wish I had time, but this really shows the zoo of the incredibly rich phenomenology that we see when stars form. It's a very rapid phenomenon, and in the 1 million year, that is very short, the sun is 4,700 million years old. It's 4.7 billion. But this is so a very short phase. A lot of things are happening. The star is absorbing matter, is ejecting matter, and all of this is now shown here in fantastic display. This is material for us for years of study, and this is again an image that was taken to demonstrate that the instrument work was not really, it's open to the public. This is something that I know people is now working on this data, but we have collected many more of these images already. This was really one of the first ones, and for us was completely amazing. Coming closer, there are the same phenomena can be seen in even greater detail, like in this class 0 protostar. I let Stefanie talk about that.
So after commissioning, we released our first images, and that actually kicked off our science operations. So we are now operating the telescope as Hubble is operated every single day, 24 hours a day, we are collecting new science. And I'm going to highlight some of our new images that we have. You can find all of these online. It's absolutely free for you to use if you need a new screensaver on your computer, or if your phone doesn't have the Carina Nebula, I don't know who you are. So I'm just going to highlight a couple of these, and I'll try to go through fairly quickly. So if you have scientific questions about them, feel free to come ask Massimo or I later. But I'm not going to go into a lot of the science details. I'm just going to highlight some of my favorite things about them. So as Massimo just said, this is a protostar. So this is actually the phase of a star where it's just becoming a star. So gas and dust are these giant clouds like the Carina Nebula that they start forming clumps. They get denser and denser, and instead of raining as the clouds in our own, or snowing, as the clouds in our own sky would do, they actually just get more and more massive because they don't have gravity pulling them down into rain onto another surface. So once that gravity gets heavy enough, atoms themselves actually start forming bigger and bigger atoms. So you start getting fusion of different atoms. So hydrogen starts fusing. And this is when the star actually becomes a star. So this is a phase where that is actually happening. And it's actually pooling all of the material from the nearby gas and dust cloud around in a disk. So if you zoom in on this image, whenever you go home tonight and you start downloading JWST images, you'll see that there's a tiny little black line going right across the middle of this hourglass, and that is actually the protostar and the disk. So it's such thick amount of dust and gas that you actually can't even see through it. But what you can see is as all of that dust and gas is starting to condense into the star and make the star a star, energy has to escape from it. And that's what we're seeing in this beautiful display, is the energy from that protostar just lighting up all of the cloud and the material that's around it. What my favorite fact about this image is, you cannot see this with the Hubble Space Telescope. You cannot see this with your own eyes. This is something that is actually illuminated only at longer wavelengths in the infrared. So it is one of my favorite images by far. The Eagle Nebula, or otherwise known as the Pillars of Creation, are absolutely fantastic. The Hubble Space Telescope image, the one on the left, is something that I grew up with and had hanging in my office through school, and always had this, impression that this was the best that you would ever get. Images weren't ever going to be better. Well, and then JWST came along and blew it away, and it's job security for me, I suppose, but it's absolutely fantastic. And the detail of what's going on in these giant gas and dust clouds, as Massimo was telling you, is something that we even didn't expect as astronomers. We are seeing phenomenon that we've never been able to study and details that we've never had, and this is absolutely fantastic. One thing I'll highlight in this particular image is if you look at the tips of the fingers in the JWST side on the right, they're red. And that's where protostars are actually starting to form. They're getting hot enough that they're actually lighting up the cloud and illuminating them with, this is actually hydrogen. So this is a fantastic example of what we can study. JWST is also studying planets around other stars. This was a challenge for us because when the mission was actually conceived, planets around other stars weren't known. There was a theory that they were there. But we actually started designing the telescope without the capability to study these objects. And now it's just one of the hottest topics in astrophysics. Fortunately, we had the insight to design some instrumentation to start studying these planets. There's over 5,000 planets now known around stars in our own galaxy. They don't look like our solar system. So what you're seeing here is the orbit of the planets of our solar system and these dashed lines compared to all of the known, at least as of 2012, exoplanetary systems. So planets orbiting the stars that we've been able to detect and observe up to this point in time. And you can see that none of them look like our solar system. And this is because this is really, really hard to do. It's really hard to study planets around other stars. And I'm going to tell you how we do this with the James Webb Space Telescope. So what we do is we stare at a star, and we wait for it to twinkle. And when it twinkles, that sometimes means that there's a planet actually passing in front of the star. So it's blocking some portion of the light of that star, making it twinkle. And how much it twinkles depends on how big that planet is, or whether it has a giant atmosphere or no atmosphere at all. And so we actually can do this type of science in our own solar system. So this is the transit of Venus, and we know Venus has a huge atmosphere, but I challenge you to find the atmosphere of Venus in front of the sun in this image. Venus has a big atmosphere, and it's very dense, and it's very chemically interesting. With our own eyes, we cannot even see the atmosphere. So we're looking at planets now thousands of light years away, trying to see if they have an atmosphere, and trying to see if they look like Earth's atmosphere, because we're crazy. But fortunately, we have fantastic instrumentation that's able to do this for us. And so what we do is we use the different wavelengths, as Massimo was showing you, and we put them on different molecules that we want to know if they're in an atmosphere. So if we want to look for Earth 2.0, we need water, carbon dioxide, methane, pick your favorite molecule in the atmosphere. And so we tune our filters to those particular wavelengths, and we watch the star twinkle. If it twinkles for water, that means there's water in the atmosphere. If it twinkles for carbon dioxide, there's carbon dioxide. And we basically take this information as the planet goes in front of its star, and we produce a spectrum. We can tell you how much of that molecule is there. And this is actually one of our science results showing you the first detection of carbon dioxide in another planet outside of our solar system. And of course, the only way to know what's going on in planets around other stars is to know what's going on in our own planets, in our own solar system. And I can tell you, we don't know what is going on to our nearest neighbors. So I'm quickly going to highlight some of my favorite solar system cases, because this is what I do for a living. And Jupiter is by far one of my favorite images. This was the first one we released for JWST. And the amazing sensitivity and dynamic range of seeing the rings of Jupiter compared to the planet itself. It's 10,000 times brighter than the rings. And we're able to observe both of them at the exact same time, studying the aurora, the great red spot, and all the dynamic atmosphere that's going on. We recently released this image of the Neptune system. The most impressive part about this image is it's photobombed by galaxies. Everywhere we look, there's galaxies. I should have been a galactic astronomer, not a planetary astronomer, but here we are. This is fantastic. So Neptune has not been seen in this type of resolution or light in over 30 years. With the Voyager flyby mission was the last time we saw the rings of Neptune. And I can tell you, it was amazing. This is like 3 minutes of JWST time. And we already saw better than we were able to see with a flyby mission 30 years ago. We see satellites, we see rings, we see clouds in the atmosphere. There's all kinds of science already being done from this one image, 3 minutes of JWST time. We've already blown the record for solar system capabilities. This is great. Sign the check. Let me retire. Let's go. Last week, we released Pandora's cluster. This is a fantastic cluster environment that's nearby. I'm just panning through the image so you can just see the extent and beauty of this particular clustered image. You see some of the galaxies are even streaked still and arced. Again, all the lensing that's happening. Fantastic resolution. Lots of tiny little red dots. Those little red dots are all galaxies too. And it either means that they're really far away, or they're really dusty. And the only way to determine that is to actually take the spectrum of it. We have to break that light apart and see if it's dust or if it's actually distance. And so this is what astronomers are doing day in and day out, because we want to see if we can detect the first galaxies of the universe with this telescope. And so by doing so, we're studying not only the evolution of our cosmic history, we want to know how galaxies formed, how they evolve. Why do we see beautiful structure in galaxies that are nearby? And then it kind of turns into fuzzy mess the further back in towards the Big Bang that we actually look. So JWST is enabling us to do new science that we haven't had access or capability of doing before. And with that, we've actually, oops, it's not going. Go. Go. Okay, all right. I'm afraid to push too many times. So this is some of our most distant candidates now that we have. So looking at redshifts of 10.5 to 12.5 redshift, which is only 350 million years after the Big Bang. And this is not even a full year of JWST science. And we're already pushing and breaking the record for the most distant objects. So more to come. I'm extremely excited about the science that's being enabled, and I can't wait for the next generation of scientists to use this telescope and tell us all the discoveries that are yet to be made. Thanks for your time.
So we have a few minutes left. We would like to hear more from them, if you will indulge us. I would like to ask Massimo a slightly personal question. I know you were assigned to this project in 1999, so that's been a while. It's most of anybody's career, 24 years. This was one of the most ambitious projects that humanity ever attempted. There were slowdowns, technical challenges, budget challenges, political challenges. What was that like, and how did you persevere all the way to here? What helped you?
Yeah, I joined the project in 1999 almost too early, because I was hired by the European Space Agency to come here, and then they realized that once I had started working that the European Space Agency had not yet signed a contract with NASA to collaborate on the project. So for 7 years I had to work on the Hubble, and I was instrument scientist for the Hubble infrared instrument before. So I've been around for a while, and I've been through all this stuff. Has been a great adventure. And there is to remain on the project, to be passionate about that. It requires like the desire of doing something great with your life. Desire of doing something great, and something that, let me say, greater than, and it's not for you even. No? It's something that you donate to the, you do. Something you do because it has to be done. I was telling my wife yesterday, we were reflecting about this. When I moved, I was in my early 40s, so I had already some expertise. You don't come here if you are just a fresh cookie. I had already done something pretty noticeable at the time. I moved here to work on Webb and the Hubble. But I was not the senior position, right? There was people in the mid-50s, 60s that were the godfathers of this idea, those that had the authority to draft the drawing that you've seen in the early slide. And I was noticing that, well, they are all retired. They were all fully retired. And some of them, let me say, fighting with Alzheimer at the time of launch. So you work on this project like you work on a cathedral. You work on this project is really at some point is not for you. No, it's because it's a great thing to do. It's because we are here together, and you start something that you may not end. You may not see to the end, but you stay. You do it because it's something great that you want to do with your life.
Thank you. Speaking of the cathedral, Stefanie, you said something very moving last week about the beauty of looking at those images and what they mean to you. And maybe you can tell us a little bit what this has felt like since, launch and commissioning, and what else we've been looking for the last year or so.
Oh, goodness. OK, so being on the project has been very emotional. It is absolutely a privilege to get to work in the position that I do. I get to see all of the images before everybody else does, which is really cool. But it's also really, really hard to be around any friends, especially with a glass of wine, because you want to tell them all the great things. So it's a lot of fun. But I will say that the beauty of these images speaks for themselves. Every time I give a talk about JWST, everyone's like, oh, it was such a good talk. And I was like, I didn't have to say anything. Look, just look. It speaks to you. It's beauty that can't be comprehended in any way. The vastness of the universe, the intricate details that we're now seeing, it's emotional. And it is something that we are now sharing with the world, and it is so fantastic to be part of this project. We've done some really cool stuff already. We've had detected some of the most distant galaxies now in the universe. We're watching star formation happen in real time. We're seeing clouds on Neptune and other planets in our solar system. It's been amazing. But one of the coolest things that we've done is we actually got to watch the DART impact mission. So I think I have some graphics showing what this mission was about. So NASA has this mission that they were able to do last year that had a satellite, a spacecraft, that was actually crashing into an asteroid system. So it's 2 asteroids. And what they're doing is for planetary defense, they were trying to move the moonlet, so the smaller of the 2 asteroids. So by moving it, it's demonstrating that if there's an asteroid coming towards Earth and it's going to implode and hit us, and dinosaur kind of event, we can go and nudge the asteroid when it's far enough away so that it doesn't actually hit us. So this was really cool, but not only was this amazing to do for a planetary defense sort of demonstration, but it was also very cool scientifically. So this was the first time JWST got to support a planetary mission, which meant we had to track an asteroid that was going really, really fast. And so this was where my job got to be the best, because I get to tell all the engineers that built this fantastic, extremely sensitive telescope that's pointing across the universe, I tell them I want to go really, really, really fast so that we can watch this asteroid blow up. And they're like, you're crazy, Stefanie. And I was like, no, we could do this, we could do this. So a lot of people actually helped work behind the scenes to prove that we could actually do this. And so we actually did observe the DART impact mission. And so what you're seeing on the left here is, it's a really quick image that's looping, I apologize. But you'll notice that it starts very, very faint. And that's right before the impact, and then it gets extremely bright, and you see this huge burst of energy. We're disentangling the information now. It's very, very hard to do because the asteroid was extremely bright. And there was so much dust that was released. We're trying to dig in through all of that dust to find out where the actual ejecta of the material from the spacecraft came from. This was also the first time that JWST observed the exact same thing as the Hubble Space Telescope. So we have simultaneous imaging that happened with the Hubble Space Telescope. So this was one of my proud moments I get to say that I was involved in. We're working on the science now. It's been amazing, and more to come for sure.
Massimo, I'll go back to you for a second. I said in the introduction you were the owner, although that's not the right word. You led the Orion Nebula project. Not the owner, because those images are for everybody. And you know, the Orion Nebula was one of the very first images that came out with the James Webb. It was part of the original 5 pictures. What is special about that region in the universe, and why are we so fond of it? Besides, you know, it looks awesome.
So the Orion Nebula, which is something that maybe not from New York, but you can see in the evening, a naked eye, is one of the most important regions in the sky, because it's the closest region to us where stars, giant stars are forming. And giant stars have a critical role in the evolution of the universe. They are rare, and they have they live a short life. They're like, I call them the James Dean of stars, right? Very, very energetic, very dynamic, and very short life in some way. Let me say that. So the Orion Nebula is the place closest to us where we see giant stars forming. It's important because when giant stars form, they are accompanied by thousands of more smaller stars, including several like the Sun, like us. Actually, we believe that our Earth formed 4.7 billion years ago in a region like that. And so it's important to understand how stars like the Sun form, how planets like us form, and in general, the entire phenomenon of star formation happens in places like the Orion Nebula. So what I do in particular, I decided for some reason to go in a direction that is not the one that many follow. I study not the supergiant, I study the super small. Because at some point in the Orion Nebula, we start seeing stars which are not even stars. They are like balls of gas that will never shine like stars, and they are very rare. They will stay there forever. They look like planets. We don't know exactly how many are there because they are very faint. Even close to us, we don't count them all. But when they are young, they are sort of more easily visible. So we want to understand these very strange ultra-small stars. They are called the brown dwarfs. The smallest brown dwarfs study in the Orion Nebula, how they form and how many are there. So that's what I do.
So we talked about star formation. We talked about exoplanets. We talked about infrared light and the earliest galaxies. Stefanie, what is the James Webb really looking for?
Everything. So we set out with this observatory to address 4 main themes. One of which is we're looking for the first stars and galaxies that formed in the universe. And so having the capability of this telescope, we're pushing farther and farther. As I've already shown you, we're already breaking our limits, and we hope to find those very first galaxies that formed. Those are going to tell us a lot about how the rest of the universe came to be, how much, fusion was happening in the stars of those galaxies. How did those galaxies evolve? How did they impact the environments around them? We want to understand how stars and planets are being formed, as we've already talked about briefly. We also want to study what planets around other stars look like, and if there are any planets that actually look like Earth. And of course, we want to study our own solar system, which is my personal passion and job. So my favorite thing that's to come, though, is all of the things that we don't know. We don't know what we don't know yet. Every time we take an image, we're learning something new. Every time we take a spectrum, we're learning something new. The discovery space is absolutely beyond. And of course, I'm a cometary scientist, so we are planning to actually study comets as well with the James Webb Space Telescope. And some of you may have heard about this green comet in the sky right now. I actually have a program to observe the green comet in about a week and a half. So stay tuned. I expect everything to be fantastic and new discoveries await.
Along those lines, where do we come from, and are we alone in the universe?
So these are humankind's biggest questions. We've been asking this for as long as we know, as long as there's been a record. And while the James Webb Space Telescope is a fantastic instrument, it is not hunting for little green men. Maybe we will find a planet that looks like Earth's. But more importantly, we want to find a planet that has something going on. We want to see a planet that has an atmosphere that is dynamic. Something is causing it to not just exist. It's being processed in some way. Processing happens in many different ways. If you think about the whole history of the Earth, going from the heavy bombardment era to how it evolved before we had any form of life here on Earth, or even if we look at the history of Mars, everything changes in very short timescales with respect to the universe. And so we want to see what that process is on another planet, whether it's volcanoes, whether it's storms, or maybe something even as interesting as
Massimo, what do you think? Are we alone in the universe, and why do we care?
I think we are the little green men. And I'm serious. Now, we are obviously one of the most ephemeral entities in reality. We appear here after 13.78 billion years ago. We have a story which is nothing, like a flash at the end of a day, of a firefly. And still we are the point where in the universe emerges something that builds telescopes. We are the point where protons, electrons, neutrons, matter, energy, whatever is there, becomes aware of itself, where the universe becomes, we are the pinnacle of the universe. We are the point where matter becomes aware of himself and looks at the rest, at what is there, with wonder, with question, with wonder that cannot really be stopped. And let me add, with reason. We build a telescope. We understand the language of reality. We understand what is behind that. After 13.8 billion years, we are here. And this, I think, is the most fascinating thing, that we are the point where the universe reflects on itself. And this is the way I understand the title of this meeting, right? Because this fills me with wonder about myself, no? And the grandeur that each one of us is. And we must be, I think we must be aware of this.
Thank you. We all like to talk. We could go on all evening. Unfortunately, we're out of time. I have one important announcement before closing this event. The Encounter is a miracle in the heart of New York City. It's both a little miracle and a big one. It's a place for all those who seek belonging. We invite you to give generously at our donation table outside this auditorium, or in a couple of clicks at newyorkencounter.org/donate. Please join me in thanking our speakers again, and especially Benedictine College that sponsored this event. Thank you all.
Nice job.